You know, what if I told you that training your attention isn't some mystical art form, but a computational problem? A problem your brain is actually perfectly designed to solve. Today, we're going to dive into the neuroscience and, yeah, the machine learning behind focus by looking at two really powerful algorithms for the mind.
So, if we're going to think about our brain as this incredibly advanced learning system, we have to start with the most basic question. How do you train an algorithm in the first place? It's not about willpower, it's not about brute force. Nope. You do it with data, and, maybe even more importantly, with feedback.
And that right there is the key. It's the absolute core of what we're talking about today. The secret isn't trying harder. It's all about giving your brain the right reward signal at exactly the right time. It's basically hacking into its own natural learning process, and we're going to explore two profoundly different ways to do exactly that.
Okay, here's our game plan. We'll start with the goal that both of these systems share. Then, we'll break down algorithm 1, which is all about rewarding that little aha moment. After that, we'll check out algorithm 2, which focuses on finding an effortless flow state. Then we'll put them head to head, and we'll finish up by asking a pretty practical question. Which one of these might be the right fit for your brain?
So first things first, what's the goal here? Well, even though their methods are totally different, both of these training protocols are trying to get you to the same place, a state of mind that has high attentional stability, that means your focus isn't jumping all over the place, and high signal clarity, where your perception is just sharp and free from all that mental noise.
All right, so here they are, our two fundamental architectures. On one side, you've got discrete reinforcement. Think of this like getting a little gold star for a specific correct action. And on the other side, we have continuous optimization. This is more like tuning an old school radio dial, you know? You're constantly making tiny adjustments to find the clearest, most efficient signal.
Let's dig into our first model and see how this thing is built.
This approach, which you'll often hear associated with the teacher Culadasa, is just a brilliant example of discrete reinforcement learning. And here's the twist. It's not about staying focused. It's all about what you do the moment you realize you're not.
So the deep science behind this is something called reward prediction error. It's a fundamental way our brains learn. Basically, when something happens that's better than you expected, like, say, suddenly realizing you've been daydreaming, your brain releases a little hit of dopamine. That dopamine signal acts like a powerful reinforcement. It essentially tells the circuits in your brain, hey, pay attention, that was important, do that again. This whole system hijacks that natural process to train our internal awareness. So here's what the training loop actually looks like in practice. Step 1, your mind wanders. Totally normal, happens to everyone. Step 2, you completely forget you were even supposed to be focusing. And then, and this is the absolute key, Step 3, you have that spontaneous aha moment. You suddenly realize you've been distracted. The training is so simple. You apply a positive, joyful reward signal right at that instant of realization.
Now, this is the part that's so counterintuitive, but it's also where the genius is. Imagine you're training a puppy. If it wanders off, but then it comes back when you call it, you don't scold it for wandering, right? Of course not. You praise it for coming back. It's the exact same principle. By rewarding the detection of the error, you're not really training focus directly. You're training your brain's own monitoring systems to get faster and faster and faster at catching distractions.
Okay, let's switch gears and look at a completely different operating system. This second algorithm, which comes from the work of Daniel P. Brown, is not about rewarding these little discrete moments. It's a continuous control loop. It treats attention like a real-time optimization problem that's always running.
The core idea here is what you could call continuous state estimation. Your brain is constantly generating a model of its own state, always trying to find the most efficient way to operate. This method teaches you to tune into that, to develop this kind of internal feeling for the sweet spot where your attention can just lock on with the least amount of effort possible. It's all about maximizing that signal-to-noise ratio.
I like to think of it as an adjustment dial. If you turn it up too high, if you apply way too much effort, your mind gets tight and just scatters into anxiety and strain. But if you turn it too low, if you're too loose, you just sink into dullness or even sleepiness. The actual skill is learning to navigate between those two failure modes, to find that perfect, balanced state right in the middle. And the payoff for finding that sweet spot? It's huge. I mean, look at this. The difference in metabolic cost is just staggering. Effortful, forceful concentration is incredibly expensive for your brain. It burns a ton of energy. But when you find that lock-in point, the energy cost just plummets. Your brain is literally designed to seek out these low-energy, high-efficiency states.
So you might be asking, where's the reward signal? Well, it's not a burst of joy like in the first model. It's what psychologists call negative reinforcement, which is just the removal of something unpleasant. That feeling of relief, of effort just suddenly dropping away while your clarity stays high, that is the reward. And the brain learns to seek out that state of blissful efficiency.
All right, this is where it gets really fun. Let's put these two powerful operating systems right next to each other, side by side, so we can really see their core architectural differences. This is fascinating stuff.
Okay, this table just lays it out perfectly. Look, algorithm 1 is event-driven. It rewards the detection of an error with positive reinforcement, a feeling of joy. The biggest mistake you can make? Scolding yourself. Now, algorithm 2 is state-driven. It rewards the state of minimal effort with negative reinforcement, a feeling of relief. And here, the biggest mistake is actually trying too hard. If we want to use a machine learning analogy, it's the difference between learning from sparse, powerful reward signals versus just continuously trying to minimize a cost function.
So this isn't just some theoretical debate, right? These different architectures might actually be better suited for different types of brains. And that leads us to a really fascinating hypothesis about what you might call neurotyping.
So let's just consider two common profiles. An ADHD-type brain, which is often characterized by a dopamine-seeking reward system, might respond incredibly well to those little hits of positive reinforcement you get in algorithm 1. Every aha moment is a rewarding little dopamine spike. But, on the other hand, an anxious brain, which often deals with high cognitive noise and a feeling of strain, might find the continuous relief and the energy reduction of algorithm 2 to be a much more effective path. It directly targets that feeling of being overtasked.
And all of this really points toward a brand new way of thinking about mental training, moving away from a one-size-fits-all model. By understanding these underlying mechanics, we can start to ask a pretty powerful question. What if the future of mental fitness isn't about finding the one best technique for everybody, but about finding the right algorithm for your own unique, personal neuro-architecture?